welcome back to my channel Study With Me. This time I'm going to explain subtopics 1.2.3 Mass Spectra. It is for higher level content under Structure 1.2 Theme 1. Please join my WhatsApp and Telegram channel as I'm planning to create a dedicated IB chemistry community where we can have live classes, a place for you to pose your questions, and I will work through them with you. Once we have a good number of students, I'll officially launch the community. Please share this channel with friends who are also studying IB chemistry. The more students who join, the more opportunities we'll have to grow and support each other in our studies. From this subtopic, you need to know how to interpret mass spectra in terms of identity and relative abundance of isotopes. The operational details of the mass spectrometer will not be assessed. So we're talking about mass spectra using mass spectrometer as an equipment that is used to determine the relative atomic masses of elements from their isotopic composition. Remember when we tried to calculate the relative atomic mass from the previous content standard level, we multiply the natural abundance and the mass, and we get the relative atomic mass from the isotope compositions, right? And this can be done by measuring the mass and abundance of isotopes using this equipment. It's called mass spectrometer. So how does it work? First, the element should be vaporized to be analyzed, then ionized by high energy electrons, where it produces positively charged ion or cation. The ionization here is very important because it will cause molecule to break up into different fragments, useful evidence about the structure of the compound. So here's the fragments. There are two fragments on the mass spectrum. So when we use the mass spectrometer, we'll get mass spectrum, and this mass spectrum, it has different fragments where we can use to determine the relative atomic mass. For example, the mass spectrum of gallium shows that in a sample of 100 atoms, 60 have a mass of 69. Okay, 60 have a mass 69, and 40 has a mass 71. Calculate the relative atomic mass by total mass divided by number of atoms. So total mass, you can do the calculation by 69 times 60 plus 40 times 71. Okay, divided by total atoms is 100. Then you get 69.80. So this is the relative atomic mass of gallium. Next, it's rubidium. So determine the relative atomic mass of rubidium from this mass spectrum. So 85, it's 77, and 87 is 23%. So the AR, it's total mass divided by number of atom. Number of atom is 177 plus 23. So 77 times 85 to calculate total mass. 23 times 87 divided by 100. You get 85.46. Okay. And next, deduce the relative atomic mass of magnesium from this mass spectrum. So we've got three fragments. Okay, for 78.6, the percentage of abundance 24. For 25 is 10.1. 26, it's 11.3. So AR would be total mass. So we'll multiply this mass times its natural abundance. So 24 times 78.6 and plus 25 times 10.1 plus 26 times 11.3 divided by 100. 100, right? The total mass, the total atoms. So 78.6 plus 10.1 plus 11.3, but usually it's always 100. So you get that 24.3. So this is the relative atomic mass of magnesium. The same thing with this, okay? So what is the AR? 23 times 80 plus 28 times 20, okay, divided by 100, you get a 24. All right, so let's go back into the subtopics explanation here, and there is a linking question is asking you about how does the fragmentation pattern of a compound in the mass spectrometer can help in the determination of its structure. Right, this is the fragmentation. Okay, this fragmentation pattern of a compound in the mass spectrometer can help to determine the structure by identifying the fragment ions. So we can analyze this M over Z, or mass charge, okay, that these mass charge values can help to determine the can help to identify the bonds and functional group. So we will do this in the very last topic or unit, and also can be done by determining the molecular weight. So the molecular ion peak, okay, this one indicates the compound's molecular weight, guiding structural inference, and also by understanding fragmentation pathways, different functional group fragment in characteristic ways, providing clues about the original molecule. So this structural information can help to determine the relative intensities of fragment ions, suggest the stability and presence of certain structure. But this question actually can be answered, and you guys will get it perfectly while we are learning about the fragmentation and pattern in terms of the data processing when we use other equipments. But this will be talk more details when we learn the data measurement. I mean, using, for example, MS, mass spectrometer, but you will get more detail in terms of this mass spectrum, okay? And also using the IR, and also another equipment. This is the NMR, okay? So you can just keep it for now, but you will understand this perfectly when we talk about data processing to determine the structure. All right, so in this video we have talked about the mass spectra, and then how to calculate the relative atomic mass from the mass spectrum, right? So thank you so much for watching. If you haven't already, please subscribe to the channel, and do not forget to share it with friends who might benefit. Be sure to join the WhatsApp and Telegram channels to stay updated on the community, where I plan to hold live classes, answer your questions, and work through IB style exam questions for each topic. Your support means everything for me, and see you in the next video.